Level 0. A compass needle trembles in someone's garage in Minnesota. Nobody's touching it. No magnets nearby. Just sitting there on a workbench, quivering like it's trying to remember which way north is supposed to be. 483 kilometers up. A satellite records a voltage spike. Lasts maybe 3 seconds. The engineer monitoring it in Colorado Springs makes a note in a log file that'll get deleted in 6 months when the database hits capacity. Standard fluctuation. Happens all the time. In Tromsø, Norway, a faint green curtain ripples across the sky at 11 p.m. A few tourists take photos. Most locals don't bother looking up anymore. None of these things are connected, except they are. They're all symptoms of the same event. The sun just exhaled in Earth's direction, and a wave of charged particles hit the magnetosphere 8 minutes after leaving the surface of our star. Not a storm, not even close. Just the constant background hum of energy that's been washing over this planet since before anything lived here to notice. Your body registered absolutely nothing. The atmosphere filtered most of it. The magnetic field deflected what got through. This is what space weather looks like when it's being polite. The problem is the sun doesn't stay polite. Sometimes it coughs, sometimes it throws things, and sometimes it does something so violent that the only reason we know about it is because trees keep better records than civilizations do. This is the floor, the baseline that never stops. Everything else on this list is what happens when that baseline becomes a scream. What happens when the sun stops whispering? Level 1. The pilot over the Pacific reaches for his radio. Static. He tries the backup frequency. More static. Check the equipment. Everything's green, all systems nominal. The radio works perfectly. The problem is 97 kilometers above him, where a wall of X-rays from the sun just stripped electrons off the ionosphere like pulling batteries out of a smoke detector. This is April 2nd, 2001. For 11 minutes, high-frequency radio on the daylit side of the planet goes silent, not broken, just temporarily unavailable because the layer of atmosphere that radio waves bounce off to travel around Earth's curve isn't there anymore. Pilots can't raise air traffic control. Ships lose contact with shore stations. Ham radio operators in Australia wonder if their equipment died. An X-class solar flare happens when magnetic fields on the sun's surface twist past the point they can hold, snap like overstressed cable, and dump the equivalent of 1 billion hydrogen bombs worth of energy into space in about 6 minutes. The light takes 8 minutes to reach Earth. No warning period, no buffer. The flare happens, and by the time we see it, the X-rays are already here. We've built a communication system that assumes the ionosphere behaves. Flight paths depend on radio contact. Maritime navigation uses signal propagation that requires a reflective upper atmosphere. GPS timing calculations factor in ionospheric delay. An X-flare doesn't break any of this. It just borrows the infrastructure for a few minutes. Except nobody asked if they could borrow it, and there's no alternate route. The ionosphere comes back. Always does within an hour or so. Radio returns. Everyone goes back to normal operation. But for those 11 minutes, a chunk of the world's communication network just stopped. Not because anything failed, but because the medium vanished. We can see flares happen in the sun. We've got satellites watching constantly. Doesn't help. The light and the disruption arrive together, which means the warning is the event. By the time you know it's happening, it's already happening. But light dissipates fast. Spread thin. What if the sun throws something with actual mass behind it? Level 2. Quebec, March 13th, 1989. 2:44 a.m. A technician at Hydro-Quebec watches a transformer overheat on his monitor. Then another. Then 6 more in sequence, like dominoes made of copper coils and insulation that suddenly can't handle the current running through them. 90 seconds later, 6 million people lose power in the middle of a Canadian winter. Not from ice on the lines, not from equipment age, from something that left the sun 30 hours earlier, 1 billion tons of magnetized plasma that slammed into Earth's magnetic field hard enough to compress it, warp it, and induce electrical currents in the ground itself. Transformers aren't designed for that. They're designed for predictable loads, alternating current from generators, scheduled demand, normal operational parameters. They are spectacularly not designed for the ground beneath them to suddenly become a conductor for currents generated by a magnetic storm 97 kilometers overhead. The longer the power line, the better it works as an antenna for geomagnetically induced currents. High-voltage transmission lines across Quebec are extremely long. In 1989, they picked up a signal they couldn't handle. Meanwhile, people in Florida are standing in their yards watching auroras. Texas sees them too. The northern lights are visible at latitudes where they shouldn't physically occur, because the magnetic field got shoved so far south that the solar wind started interacting with the atmosphere over places it normally never touches. Grid operators see auroras in Florida and immediately know what it means. The system is being stressed by something invisible, something outside the design parameters, something they can't turn off or reroute. You just have to wait for it to stop. The storm lasted hours. Power came back within a day. We got lucky. The coronal mass ejection hit at an angle. Some of the energy deflected. If the magnetic orientation had been slightly different, if the impact had been head-on, more grids would have failed. More transformers were destroyed. Longer outages? 1989 wasn't even the worst one. The worst one happened before we had power grids to break. What happens when the sun throws something truly absurd? Something aimed directly at Earth with magnetic fields aligned perfectly. Level 3, September 1st, 1859. Richard Carrington, British astronomer, is sketching sunspots. Standard morning work. When he sees something that shouldn't be visible through his equipment, a white light flare bright enough to punch through his telescope's solar filter in broad daylight. He watches it for 5 minutes. Make notes. The flare fades. 17 hours later, the sky caught fire. Auroras appeared over Cuba, over Hawaii, so bright in the Rocky Mountains that gold miners woke up at 1 a.m., thought it was dawn, and started making breakfast. Telegraph operators reported sparks jumping between their equipment and metal surfaces. Some disconnected the batteries powering their systems entirely and found the telegraphs kept working anyway, running on current induced directly by the storm. Paper caught fire at a telegraph station in Boston. Not from equipment failure, from electrical charge in the air finding something flammable. One operator in Boston sent messages to Portland for 2 hours on auroral current alone. No battery, just the storm. The Carrington event is the top of what we've directly witnessed. A coronal mass ejection so massive and so magnetically aligned with Earth's field that it essentially short-circuited the magnetosphere. Magnetometers across the planet recorded disturbances. Compass needles swung wildly. Sailors navigating by magnetic heading found their instruments temporarily useless, pointing at nothing in particular. In 1859, our most advanced electrical infrastructure was the telegraph. Copper wires, basic circuits, simple batteries, that's all we had. The Carrington event fried that system, and it barely mattered to most people because almost nobody depended on electricity for survival. We're no longer those people. A Carrington-level event today would blow transformers across entire continents. Not trip breakers. Physically destroy the hardware. Transformers take 12 to 18 months to manufacture. They require specialized facilities to transport. You can't just order a replacement. The US has roughly 2,000 extra high voltage transformers in the grid. A direct G5 hit could damage hundreds at once. There's no warehouse full of spares sitting in Kansas. Satellites would fail. Not all of them, but enough that GPS degrades, communication links go intermittent, weather forecasting loses coverage. Economic impact studies for a direct Carrington repeat land somewhere between $1 and $2 trillion in the first year. Recovery time? A decade. Not because the storm lasts that long, it'd be over in days, but because the damage cascades through every system that assumes reliable electricity exists, which in 2026 is essentially all of them. The probability of a Carrington-scale event is about 1 to 2% per decade. Sounds low, except it's not per century. Per decade. We've gone 165 years without one. The odds aren't improving. Even a superstorm has to travel through space first. It takes 18 to 72 hours for the plasma to reach Earth after leaving the sun. We can see the CME coming. There's some warning, even if it's measured in hours instead of days. The next level doesn't give you that luxury. Level 4, October 28, 2003. A solar flare erupts. 8 minutes later, X-rays hit Earth. Expected standard physics. 11 minutes after that, a radiation detector on a satellite near Mars records a spike. The particles are moving at nearly half the speed of light. Solar energetic particle events happen when a flare or CME accelerates protons to relativistic speeds and launches them outward in a directional beam. If Earth happens to be in that beam's path, the particles arrive minutes to hours after the flare, long before the slower plasma bulk shows up. They don't interact much with the ground. The atmosphere at low altitude stops them, but anything in orbit gets irradiated. Astronauts on the ISS sheltered in the most shielded modules during October 2003. Radiation outside spiked high enough that a spacewalk would have exceeded safe exposure limits in minutes. Had someone been outside when the particles arrived, they would have absorbed a dose equivalent to several chest X-rays per minute. Not immediately lethal, but enough to cause radiation sickness if it continued, enough to meaningfully increase cancer risk. The 6 people on the ISS aren't the issue. The real problem is the 7,000 plus active satellites in orbit. Most are radiation hardened, but hardened is relative. An S5 event delivers particle flux that degrades electronics over time and causes bit flips, random memory errors from a single proton hitting a transistor the wrong way. In 2003, over a third of Earth observation satellites reported anomalies. Some went into safe mode. A Japanese satellite lost function entirely. GPS accuracy degraded because satellite clocks drifted slightly from radiation-induced errors. Airlines rerouted flights over polar regions where radiation exposure peaks. Pilots and crew at cruising altitude absorbed measurably higher doses than normal. Not dangerous for one flight, but cumulative exposure adds up, and an S5 event dumps a year's worth of background radiation into a few hours. Particle events can happen without a CME. A strong flare alone can generate them, which means there's no 18-hour warning. The flare occurs and the particles are already on their way. You either handle it or you don't. Satellites either survive or they fail. Astronauts shelter in place. Pilots reroute if there's time. Particles still follow rules, travel in relatively straight lines, interact with magnetic fields predictably. But what if the source isn't the sun? What if it's something farther out? Something that's been traveling for thousands of years before it gets here? Level 5. This hasn't happened yet, but it will. Sometime in the next few 100,000 years, could be tomorrow in astronomical terms, could be far enough out that no human alive today needs to worry about it. A massive star within a few dozen light-years of Earth will run out of fuel, collapse, and explode as a supernova. When the light reaches us, it'll outshine the full moon, cast shadows at midnight, stay visible during the day for weeks. Astronomers will lose their collective minds. The public will panic briefly, then mostly go back to normal after nothing immediately explodes. The light isn't the problem. Days to weeks after the visible light show, depending on distance, a sustained wave of high-energy cosmic rays hits Earth's atmosphere. Particles accelerated to near light speed by the supernova's shockwave. Not a brief spike like solar particles, a bombardment lasting years. The atmosphere absorbs most of it, but ozone breaks down in the process. UV radiation at the surface increases. Mutation rates climb in surface organisms. Cancer rates in humans tick measurably upward. Satellites experience elevated failure rates. Electronics need extra shielding that most don't have. We know this happened before. Around 2.6 million years ago, iron-60 isotopes started appearing in ocean sediment cores. Iron-60 is produced almost exclusively in supernovae. The timing lines up with a minor extinction event in marine megafauna, not a mass die-off, just a noticeable uptick in things dying, particularly larger animals. The supernova was likely 150 to 300 light-years away, far enough that Earth wasn't sterilized, close enough to leave fingerprints in the rock. Betelgeuse, a red supergiant 650 light-years away, is the one everyone watches. Overdue to explode in astronomical terms, which could mean tomorrow or 100,000 years from now. Astronomy doesn't do precision timelines well. At that distance, a Betelgeuse supernova would be spectacular, but not dangerous. Closer candidates exist. Ik Pegasi, 150 light-years away, will eventually go supernova. Not for millions of years. Spica, 250 light-years out, same story. We don't have a complete inventory of every massive star within threatening range. Some are obscured by dust, some are in survey gaps. The next nearby supernova could be a star we've cataloged and dismissed, or one we haven't noticed. When it happens, and it will eventually, we'll watch the light, measure the particle flux, adapt where we can, and hope distance is on our side. Because if it wasn't, adaptation doesn't really apply anymore. Just survival math. Supernovae are rare. Odds of one close enough to matter during human civilization's run are low. The sun, on the other hand? The sun has one more card it might have played before, back when nobody was around to write it down. Level 6, 774 AD. Somewhere in what would eventually become Japan, a tree grows. Nothing special about it. Just a tree, doing tree things, adding a ring every year the way trees do. In 2012, scientists analyzing the tree's rings found something wrong. The carbon-14 level in the 774 ring was 12 times higher than normal. Carbon-14 forms when cosmic rays hit the atmosphere. A spike that large suggests cosmic ray flux far beyond anything we've measured in modern history. At first, researchers thought it might be a nearby supernova, but there's no record anywhere of an unusually bright star that year. No mentions in European chronicles, nothing in Middle Eastern astronomy records, nothing in Chinese court documents that obsessively tracked celestial events. The sun threw something at Earth in 774 AD that was significantly worse than Carrington. We only know because trees keep records better than humans did in the 8th century. A second event shows up in tree rings from 993 AD. Same signature, slightly weaker, but still way beyond modern solar activity. Superflares coupled with extreme coronal mass ejections, something the sun does rarely, maybe once every few thousand years, but not never. The 774 event may have been 10 to 100 times more energetic than Carrington. At that scale, geomagnetic storms wouldn't just damage infrastructure, they'd dismantle it. Every power grid on the daylit hemisphere fails simultaneously. Satellites disabled or destroyed. Even underground fiber optic lines could suffer data loss from induced currents in their shielding. We wouldn't get much warning. Maybe 15 minutes from flare to particle impact, maybe 12 hours for the bulk plasma. Enough time to shut down vulnerable systems if every protocol works perfectly and every operator responds instantly. Not enough time to do anything meaningful about food distribution, water treatment, hospital backup power, supply chains that assume just-in-time delivery. The economic collapse wouldn't come from the storm. It'd come from the realization days later that repair timelines are measured in years. Modern cities can't sustain themselves without constant external input. Food, water treatment, medical supply chains, all of it assumes electricity exists. Remove power for a month and cities stop functioning. Remove it for a year and population distribution shifts because urban centers can't support themselves. The sun has done this. The tree rings prove it. The question is whether we'll be here watching when it does it again. Researchers monitor solar activity, model coronal behavior, and maintain satellite networks. Early warning time for a Miyake-level event? Hours at best. You can't retrofit a grid in hours. You can't shield satellites in hours. You take the hit and spend the next decade rebuilding, assuming rebuilding is the word that applies. Everything so far operates within known physics. Particles, magnetic fields, plasma. We understand those mechanisms even if we can't stop them. There's one more level. It doesn't come from the sun. Comes from elsewhere in the galaxy, traveling at 99.9% the speed of light, carrying energy that makes everything else look like background static. Level 7. A gamma-ray burst happens when a massive star collapses into a black hole, or when two neutron stars spiral into each other and merge. For a few seconds, sometimes less, the dying star releases more energy than our sun will produce in its entire 10 billion year lifespan, focused into two narrow jets shooting out from the magnetic poles at near light speed. If one of those jets happens to be pointed at Earth, the gamma rays cross whatever distance separates us, could be 1,000 light years, could be 10,000, and arrive all at once. No warning. The event causing it happened centuries or millennia ago, depending on distance. The light and the gamma rays travel together. By the time we detect it, it's already hitting us. The gamma ray flux strips the ozone layer on the daylit hemisphere in seconds. Don't degrade it, remove it. UV radiation at the surface spikes to levels causing immediate DNA damage in exposed cells. Anything on the daylit side without shelter gets a radiation dose severe enough to cause cellular breakdown within minutes. Phytoplankton in the surface ocean, base of the marine food chain, die en masse. Atmospheric chemistry shifts as nitrogen and oxygen molecules break apart and recombine into nitrogen dioxide, creating a brownish haze lasting years. A 10-second burst from 6,000 light-years away would deliver radiation equivalent to a nuclear detonation to half the planet. Not from heat, not from blast pressure, just ionizing radiation stripping electrons off atmospheric molecules and cascading down through every layer until it reaches the ground. The Ordovician extinction, 450 million years ago, killed 85% of marine species. One hypothesis, gamma-ray burst. The fossil record shows sudden die-off concentrated in shallow water species and phytoplankton-dependent organisms. Timing fits, mechanism fits. Can't prove it definitively, but the math works. We track some nearby candidates. WR-104, a Wolf-Rayet star 8,000 light-years away, is a binary system that might, emphasis on might, have one rotational pole aimed vaguely in our direction. If it goes supernova and produces a gamma-ray burst and we're in the line of fire, there's no warning. The burst and the visible light arrive simultaneously. One moment, normal sky. Next moment, half the planet is being sterilized. Odds are extremely low. The galaxy is very large. Most bursts point away from us. The ones we detect are usually billions of light-years distant, safely far away. But extremely low isn't zero. If it happens, the burst lasts seconds. Atmospheric damage lasts years. The extinction cascade lasts longer. There's nothing to do about it. No sheltering, no rerouting, no hardening infrastructure. You just hope that when a massive star within a few thousand light-years collapses, its jets point literally anywhere else.